Assalamualaikum, very good morning. So we are going to continue chapter 5, which is the last topic in the subject signal system, which is Z transform. So for this chapter 5, there are going to be three main topics, which is on the definition of Z transform. What are the regions of convergence? So what are the regions of convergence in the Z transform and the inverse Z transform? Okay, so let's go and see what are the definition of Z transform. So if you see here is that Z transform is actually the represent the complex sinusoidal discrete time signal offered by the discrete time Fourier transform DTFT, which is you have learned in chapter 4 in terms of complex exponential. So meaning that what you have learned in chapter 4, which is on the discrete time Fourier transform, you're going to actually use it in terms of complex exponential. So when you convert it into the complex exponential, then we are going to use it as the method Z transform. So similar to the Laplace transform, the Z transform can be considered as the extension of the discrete time Fourier transform. So you have learned what is Laplace transform in subject control subject. So Laplace transform is you have learned it in the S plane or S domain. So in for the Z transform is that you are going to learn the using the method of Z transform in the Z domain or Z plane. So the last one is that the Z transform changes the system difference equation into algebraic equation in the Z transform domain, which give the complete solution in one step. So meaning that there are mainly three ways three methods that you can use when you have a continuous time signal. You can either use, first one is Laplace transform. So this one you have learned in control subject. Second one is that you can use the discrete time Fourier transform, which is this one. For the discrete time Fourier transform is that is in frequency domain. Okay, and the last one is that you use the Z transform. So Z transform is actually similar to what you have learned in the Laplace transform, but it is actually converting from S domain to Z domain. Okay, normally in control subject, when you apply it to a real-time controller, so we are going to use the Z transform more frequently. So let's see what is Z transform, which is normally we call it as the discrete time signal. So first one is that you have learned that time can be actually defined as in either a signal can be defined in two ways, with either time domain or frequency domain. So for the frequency domain, you have learned this discrete time Fourier series and the discrete time Fourier transform. So Fourier series is you have learned in chapter 3 and Fourier transform you have learned in chapter 4. Okay, so if you go back and look at the notes for discrete time Fourier transform is that we have the transformation pair. So for the transformation, for the Z transform is actually representing the discrete time Fourier series signal, so it's in discrete time. So if you look back at the equation for the discrete time Fourier transform, you have the equation x e j omega equivalent to summation of x n e minus j omega n. So which means that if you were to actually convert this to the Z transform, so you're going to substitute the value e j omega, which is this value, okay, equivalent to Z. So you're going to substitute that, so that's where you will get the equation of Z transform. So x Z equivalent to summation of x n Z minus n. So this is the equation of Z transform. Okay, so for similar to what you have learned in the Fourier transform and Fourier series, you have both the Fourier transform equation, which is given by this equation 1, and you have the inverse Fourier Z transform, which is given by this equation. Okay, so you don't need to memorize it because in the exam it's given, you can actually refer to books. Okay, so next we are going to look at how to actually draw the Z transform, which can be expressed in the polar form. So if you remember in chapter 1 previously, I have explained about the expression of a signal in polar form. So you have the real value and the imaginary value over here. Okay, so after you substitute z equal to r e j omega, so r is the real value, okay, and e j omega is the imaginary value. So you can actually plot that. For example, if you have the radius here is 1, so you have a radius of 1, which is, we call it as the unit circle. So for the z plane is that you will have a unit circle which is 1 with value 1, and then you have the real value and the imaginary value. So that's where you can actually represent or express the z transform in polar form by this equation. So z is actually equivalent to r e j omega. Okay, so this one is referring to this plotting. So this shows the z transform table. So these are the common pairs of the z transform. So for today, we are going to look at all of this signal and these few signals. So how you can actually prove each of these signals, and later on how to actually apply it into the exercises or the question given. Okay, next we are going to go to the region of convergence. So for the region of convergence is that for any sequences, the set value of z for which the z transform converge is known as the region of convergence. So what does it mean by convergence? So imagine that if you have two lane here, okay, two lane. Normally if two lane here, so there are two lane, okay, two lane. Imagine that if you have two lane and then suddenly there is a construction over here, so you have cone over here, so it means that this lane will keep this part and this lane will actually converge to this lane, so it means that this one will be closed. So this is what it means by convergence. So convergence is that where you have two signal which is overlapping with each other, means that the region is overlapping with each other. Okay, so and one important issue is that for the z transform is that not all sequences will converge. Okay, so let's see what does it mean by this. Okay, so let's go and see what are the rules of the region of convergence. Okay, so if the region of convergence include the unit circle, Fourier transform sequence also converge and the system is stable. So what does it mean? So I had explained just in the previous slide is that you have the z plane. So you have the real value and the imaginary value. Okay, unit circle means that you have the unit circle with the radius 1 and you have a unit circle here. Okay, so it says here is that the region of convergence include the unit circle, then means that the sequence also converge and system is stable. What it means that later on when you plot the signal, maybe example you have z value is more than 1/2. So 1/2 is actually signal over here, radius over here. So you have 1/2 here radius. So more than 2 means that you have this area, right? This area. Okay, more than half lah. So if you see here, the area that actually sketched, that's actually include the unit circle, right? So you have the unit circle over here. So it's including unit circle. So it means that when you have the area which is include the unit circle, then the system is stable. Okay, so that is what it means by the rules of ROC, the first rule. And if it doesn't include the unit circles, means that Fourier transform does not converge. Does not converge means that does not overlap lah. So later on you might find out that there are two regions in a signal. Okay, maybe one signal you have z more than 1/2, and another one is z less than 1/3. Okay, so less than 1/3 is in the middle here, but it's smaller than 1 over 3. So it's actually at the center here. So does this signal and this signal converge? Overlapping? No. So it means that if it's not overlapping, the two signal does not overlapping, or the two area does not overlap, then the signal is not stable. Okay. So let's just see about regarding the stability. So we were talking about the Z transform, about the stability. Means that for the Z transform is that when you have the region of convergence, which include the unit circle. Okay, unit circle 1. Okay, so let's see if you can remember for the Laplace transform. So for Laplace transform is that you have the S-plane and you have the real and imaginary, if you remember. And then for example, in control 1, you have learned about plotting the rod locus. Then when you plot the rod locus is that you either plot the poles and 0 in the left side, right? Remember, in the left side area. Okay, so if you plot the poles and 0 in the left hand side area, it means that the system is stable. If you were to calculate and then for some reason that you plot the 0 is on the right side, then automatically you know that the system is not stable, or the signal is not stable. Okay, so in contrast to the Z transform over here, down here, if you see for the first one, okay, I have a unit circle here. I draw the unit circle over here. So let's see how does it look like if the system is stable. So if the system is stable means that I have the unit circle is the one with the red line. So 1. Okay, so I have a signal, the area which is, for example, this one is 1 over 4 example. Sorry, 1 over 8. Sorry, 2 over 3 lah. Okay, 2 over 3. More than 2 over 3. So means that if I plot this one, which is the gray area, so the gray area actually includes the unit circle. So means that the system is stable. In contrast, if you see this right diagram here, okay, if you see here is that I have the unit circle 1 over here, which is the red circle here. But however, this area which is being highlighted with gray area does not include the unit circle. So it means that the system is not stable. Okay? So there are 3 types of region of convergence. Okay, the first one is the inward region of convergence. So inward region of convergence is that when you have Z less than A value. So for example, this area is A. So we have Z less than A. Okay. Second one is that you have the outward region of convergence. So outward region of convergence means that if you have this radius A, so you have Z more than A. Okay, so it's moving outward. And the third one is that if you have, for example, this one is A and this one is B. Okay, so this is what we call as ring or donut shape region of convergence. Means that you have Z over here, Z is less than B, but is more than A. Okay, so this is what we call as the ring shape region of convergence.